Basalt.
Basalt is a common extrusive igneous rock formed from the rapid cooling of basaltic lava exposed at or very near the surface of a planet or moon. By definition, basalt is an aphanitic igneous rock with less than 20% quartz and less than 10% feldspar void by volume, and where at least 65% of the feldspar is in the form of plagioclase. Basalt is usually grey to black in color, but rapidly weathers to brown or rust red due to oxidation of its mafic, iron-rich, minerals into rust. Although usually characterized as dark, basaltic rocks exhibit a wide range of shading due to regional geochemical processes. Indeed, some basalts are quite light-colored, in some cases superficially resembling rhyolite to untrained eyes. Basalt almost always has a fine-grained mineral texture due to the molten rock cooling too quickly for large mineral crystals to grow, although it can sometimes be porphyritic, containing the larger crystals formed prior to the extrusion that brought the lava to the surface, embedded in a finer-grained matrix. Basalt with a vesicular or frothy texture is called scoria, and forms when dissolved gases are forced out of solution and form vesicles as the lava decompresses as it reaches the surface. On Earth, most basalt magmas are formed by decompression melting of the mantle. Basalt commonly erupts on Io, the third largest moon of Jupiter, and has also formed on Earth's moon, Mars, Venus, and the asteroid Vesta. Source rocks for the partial melts probably include both peridotite and pyroxenite, for example, Sobolev al. 2007. The crustal portions of oceanic tectonic plates are composed predominantly of basalt, produced from upwelling mantle below ocean ridges. The term basalt is at times applied to shallow intrusive rocks with a composition typical of basalt, but rocks of this composition with a pheneritic, coarse, ground mass are generally referred to as diabase, also called dolerite, or gabbro. In the Hadean and Archean, and the early Precambrian, eras of Earth's history, the chemistry of erupted basalts was significantly different from today's, due to crustal and asthenosphere differentiation issues, so much so that there is an alternate, but less well-known, name for this kind of basalt.
Etymology.
The word basalt is ultimately derived from late Latin basalts, misspelling of L-basanites, very hard stone, which was imported from ancient Greek basanites, from basanos, touchstone, and originated in Egyptian Bahan slate. The modern petrological term basalt describing a particular composition of lava-derived rock originates from its use by Georgius Agricola in 1556 in his famous work of Mining and Mineralogy de Re Metallica, Libri 12. Agricola applied basalt to the volcanic black rock of the Schlossberg, local Castle Hill, at Stolpen, believing it to be the same as Pliny the Elder's very hard stone.
Uses.
Basalt is used in construction, for example as building blocks or in the groundwork, making cobblestones, from columnar basalt, and in making statues. Heating and extruding basalt yields stone wool, an excellent thermal insulator.
Types.
Thallitic basalt is relatively rich in silica and poor in sodium. Included in this category are most basalts of the ocean floor, most large oceanic islands, and continental flood basalts such as the Columbia River Plateau, MORB. Mid-ocean ridge basalt is characteristically low in incompatible elements. MORB is commonly erupted only at ocean ridges. MORB itself has been subdivided into varieties such as NMORB and EMORB, slightly more enriched in incompatible elements. High alumina basalt may be silica undersaturated or oversaturated, see normative mineralogy. It has greater than 17% alumina, Al2O3, and is intermediate in composition between thalliite and alkali basalt. The relatively alumina-rich composition is based on rocks without phenocrysts of plagioclase. Alkali basalt is relatively poor in silica and rich in sodium. It is silica undersaturated and may contain feldspathoids, alkali feldspar and phlogopite. Bonanite is a high magnesium form of basalt that is erupted generally in back arc basins, distinguished by its low titanium content and trace element composition.
Petrology.
The mineralogy of basalt is characterized by a preponderance of calcic plagioclase feldspar and pyroxene. Olivine can also be a significant constituent. Accessory minerals present in relatively minor amounts include iron oxides and iron titanium oxides, such as magnetite, ulvaspinel, and ilmenite. Because of the presence of such oxide minerals, basalt can acquire strong magnetic signatures as it cools, and paleomagnetic studies have made extensive use of basalt. In thalliatic basalt, pyroxene, augite and orthopyroxene or pigeonite, and calcium-rich plagioclase are common phenocryst minerals. Olivine may also be a phenocryst, and when present, may have rims of pigeonite. The ground mass contains interstitial quartz or tridymite or cristobalite. Olivine thalliite has augite and orthopyroxene or pigeonite with abundant olivine, but olivine may have rims of pyroxene and is unlikely to be present in the ground mass. Alkali basalts typically have mineral assemblages that lack orthopyroxene but contain olivine. Feldspar phenocrysts typically are labradorite to andesine in composition. Augite is rich in titanium compared to augite in thalliatic basalt. Minerals such as alkali feldspar, yacite, nepheline, sodalite, phlogopite mica, and apatite may be present in the ground mass. Basalt has high liquidus and solidus temperatures. Values at the Earth's surface are near or above 1200 DEGC, liquidus, and near or below 1000 DEGC, solidus. These values are higher than those of other common igneous rocks. The majority of thalliites are formed at approximately 50 to 100 km depth within the mantle. Many alkali basalts may be formed at greater depths, perhaps as deep as 150 to 200 km. The origin of high alumina basalt continues to be controversial, with interpretations that it is a primary melt and that instead it is derived from other basalt types, for example, Ozerov, 2000.
Geochemistry.
Relative to most common igneous rocks, basalt compositions are rich in MgO and Ca and low in CO2 and the alkali oxides, that is, Na2O plus K2O, consistent with the TAS classification. Basalt generally has a composition of 45 to 55 Wt% CO2, 2 to 6 Wt% total alkalis, 0.5-2.0 Wt% TO2, 5 to 14 Wt% FeO and 14 Wt% or more Al2O3. Contents of Ca are commonly near 10 Wt%. Those of MgO commonly in the range 5 to 12 Wt%. High alumina basalts have aluminium contents of 17 to 19 Wt% Al2O3. Beninites have magnesium contents of up to 15% MgO. Rare feldspar-rich mafic rocks, akin to alkali basalts, may have Na2O plus K2O contents of 12% or more. The abundances of the lanthanide or rare earth elements, REE, can be a useful diagnostic tool to help explain the history of mineral crystallization as the melt cooled. In particular, the relative abundance of europium compared to the other REE is often markedly higher or lower, and called the europium anomaly. It arises because U2+ can substitute for Ca2+ in plagioclase feldspar, unlike any of the other lanthanides, which tend to only form 3+ cations. MORB basalts and their intrusive equivalents, gabbros, are the characteristic igneous rocks formed at mid-ocean ridges. They are thalliites particularly low in total alkalis and in incompatible trace elements, and they have relatively flat REE patterns normalized to mantle or chondrite values. In contrast, alkali basalts have normalized patterns highly enriched in the light REE, and with greater abundances of the REE and of other incompatible elements. Because MORB basalt is considered a key to understanding plate tectonics, its compositions have been much studied. Although MORB compositions are distinctive relative to average compositions of basalts erupted in other environments, they are not uniform. For instance, compositions change with position along the mid-Atlantic ridge, and the compositions also define different ranges in different ocean basins. Hoffman, 2003. Isotope ratios of elements such as strontium, neodymium, lead, hafnium, and osmium in basalts have been much studied, so as to learn about evolution of the Earth's mantle. Isotopic ratios of noble gases, such as 3He/4He, are also of great value. For instance, ratios for basalts range from 6 to 10 for mid-ocean ridge thalite, normalized to atmospheric values, but to 15-24+ for ocean island basalts thought to be derived from mantle plumes.
Morphology and textures.
The shape, structure and texture of a basalt is diagnostic of how and where it erupted, whether into the sea, in an explosive cinder eruption or as creeping Pahahio lava flows, the classic image of Hawaiian basalt eruptions.
Subaerial eruptions.
Basalt which erupts under open air, that is, subaerially, forms three distinct types of lava volcanic deposits: scoria, ash or cinder, bryxia, and lava flows. Basalt in the tops of subaerial lava flows and cinder cones will often be highly vesiculated, imparting a lightweight frothy texture to the rock. Basaltic cinders are often red, colored by oxidized iron from weathered iron-rich minerals such as pyroxene. AA types of blocky, cinder and bryxia flows of thick, viscous basaltic lava are common in Hawaii. Pahahio is a highly fluid, hot form of basalt which tends to form thin aprons of molten lava which fill up hollows and sometimes forms lava lakes. Lava tubes are common features of Pahahio eruptions. Basaltic tuff or pyroclastic rocks are rare but not unknown. Usually basalt is too hot and fluid to build up sufficient pressure to form explosive lava eruptions, but occasionally this will happen by trapping of the lava within the volcanic throat and build-up of volcanic gases. Hawaii's Mauna Loa volcano erupted in this way in the 19th century, as did Mount Taurora, New Zealand in its violent 1886 eruption. Mauna volcanoes are typical of small basalt tuffs, formed by explosive eruption of basalt through the crust, forming an apron of mixed basalt and wall rock bryxia and a fan of basalt tuff further out from the volcano. Amygdaloidal structure is common in relic vesicles and beautifully crystallized species of xylides. Quartz or calcite are frequently found.
Columnar basalt.
During the cooling of a thick lava flow, contractional joints or fractures form. If a flow cools relatively rapidly, significant contraction forces build up. While a flow can shrink in the vertical dimension without fracturing, it can't easily accommodate shrinking in the horizontal direction unless cracks form. The extensive fracture network that develops results in the formation of columns. The topology of the lateral shapes of these columns can broadly be classed as a random cellular network. These structures are predominantly hexagonal in cross-section, but polygons with 3 to 12 or more sides can be observed. The size of the columns depends loosely on the rate of cooling. Very rapid cooling may result in very small, less than 1 cm diameter, columns, while slow cooling is more likely to produce large columns.
Submarine eruptions. Pillow basalts.
When basalt erupts underwater or flows into the sea, contact with the water quenches the surface and the lava forms a distinctive pillow shape, through which the hot lava breaks to form another pillow. This pillow texture is very common in underwater basaltic flows and is diagnostic of an underwater eruption environment when found in ancient rocks. Pillows typically consist of a fine-grained core with a glassy crust and have radial jointing. The size of individual pillows varies from 10 cm up to several meters. When Pahahio lava enters the sea it usually forms pillow basalts. However, when lava enters the ocean it forms a littoral cone, a small cone-shaped accumulation of tufaceous debris formed when the blocky lava enters the water and explodes from built-up steam. The island of Surtsey in the Atlantic Ocean is a basalt volcano which breached the ocean surface in 1963. The initial phase of Surtsey's eruption was highly explosive, as the magma was quite wet, causing the rock to be blown apart by the boiling steam to form a toughened cinder cone. This has subsequently moved to a typical Pahahio-type behavior. Volcanic glass may be present, particularly as rinds on rapidly chilled surfaces of lava flows, and is commonly, but not exclusively, associated with underwater eruptions.
Life on basaltic rocks.
The common corrosion features of underwater volcanic basalt suggest that microbial activity may play a significant role in the chemical exchange between basaltic rocks and seawater. The significant amounts of reduced iron, Fe2, and manganese, Mn2, present in basaltic rocks provide potential energy sources for bacteria. Recent research has shown that some Fe2, oxidizing bacteria cultured from iron sulfide surfaces are also able to grow with basaltic rock as a source of Fe2. In recent work at Loisea Mount, Fe and Mn oxidizing bacteria have been cultured from weathered basalts. The impact of bacteria on altering the chemical composition of basaltic glass, and thus, the oceanic crust, and seawater suggest that these interactions may lead to an application of hydrothermal vents to the origin of life.
Distribution.
Basalt is one of the most common rock types in the world. Basalt is the rock most typical of large igneous provinces. The largest occurrences of basalt are in the ocean floor that is almost completely made up by basalt. Above sea level, basalt is common in hotspot islands and around volcanic arcs, especially those on thin crust. However, the largest volumes of basalt on land correspond to continental flood basalts. Continental flood basalts are known to exist in the Deccan Traps in India, the Chilcotin Group in British Columbia, Canada, the Parana Traps in Brazil, the Siberian Traps in Russia, the Karoo Flood Basalt Province in South Africa, the Columbia River Plateau of Washington and Oregon. Many archipelagos and island nations have an overwhelming majority of its exposed bedrock made up by basalt due to being above hotspots, for example, Iceland and Hawaii. Ancient Precambrian basalts are usually only found in fold and thrust belts, and are often heavily metamorphosed. These are known as greenstone belts, because low-grade metamorphism of basalt produces chlorite, actinolite, epidote and other green minerals.
Lunar and Martian basalt.
The dark areas visible on Earth's moon, the lunar maria, are plains of flooded basaltic lava flows. These rocks were sampled by the manned American Apollo program, the robotic Russian lunar program, and are represented among the lunar meteorites. Lunar basalts differ from their terrestrial counterparts principally in their high iron contents, which typically range from about 17 to 22 Wt% Fe0. They also possess a stunning range of titanium concentrations, present in the mineral ilmenite, ranging from less than 1 Wt% TO2, to about 13 Wt%. Traditionally, lunar basalts have been classified according to their titanium content, with classes being named high T, low T, and very low T. Nevertheless, global geochemical maps of titanium obtained from the Clementine mission demonstrate that the lunar maria possesses a continuum of titanium concentrations, and that the highest concentrations are the least abundant. Lunar basalts show exotic textures and mineralogy, particularly shock metamorphism, lack of the oxidation typical of terrestrial basalts, and a complete lack of hydration. While most of the Moon's basalts erupted between about 3 and 3.5 billion years ago, the oldest samples are 4.2 billion years old, and the youngest flows, based on the age dating method of crater counting, are estimated to have erupted only 1.2 billion years ago. Basalt is also a common rock on the surface of Mars, as determined by data sent back from the planet's surface and by Martian meteorites.
Alteration of basalt. Metamorphism.
Basalts are important rocks within metamorphic belts, as they can provide vital information on the conditions of metamorphism within the belt. Various metamorphic facies are named after the mineral assemblages and rock types formed by subjecting basalts to the temperatures and pressures of the metamorphic event. These are blues schist facies, eclogite facies, granulate facies, Griens schist facies, xylite facies. Metamorphosed basalts are important hosts for a variety of hydrothermal ore deposits, including gold deposits, copper deposits, volcanogenic massive sulfide ore deposits and others.
Weathering.
Compared to other rocks found on Earth's surface, Basalts weather relatively fast. The typically iron-rich minerals oxidize rapidly in water and air, staining the rock a brown to red color due to iron oxide, rust. Chemical weathering also releases readily water-soluble cations such as calcium, sodium and magnesium, which give basaltic areas a strong buffer capacity against acidification. Calcium released by basalts binds up CO2 from the atmosphere forming CaCO3, acting thus as a CO2 trap. To this it must be added that the eruption of basalt itself is often associated with the release of large quantities of CO2 into the atmosphere from volcanic gases. Carbon sequestration in basalt has been studied as a means of removing carbon dioxide, produced by human industrialization, from the atmosphere. Underwater basalt deposits, scattered in seas around the globe, have the added benefit of the water serving as a barrier to the re-release of CO2 into the atmosphere.